Howdy, today I'm Flipping Science, looking at combustion, thermochemical equations, and incomplete combustion.
Tilt my hat at the sun, and the shadows they burn down. Like me, and I'll burn for you, and the love song never stops.
So science understands we're going to look at the complete combustion of fuels containing carbon and hydrogen produces carbon dioxide, water, and energy. So you need to write thermochemical equations for the complete combustion of fuels. Then incomplete combustion is more likely with longer chain carbon-based fuels, so explain why that is and talk about the undesirable consequences of incomplete combustion. So combustion is burning things. We rely on burning things to heat our homes, cook food, provide electricity in many places. This is a typical example of a combustion reaction. We have a fuel containing carbon and hydrogen, we're burning an oxygen, and our only products are carbon dioxide and water. So this is what we call complete combustion. And that's the nice pretty blue flame we have over here. Whereas over here we have a yellow flame, that's the result of incomplete combustion. We're going to talk about that later on. So as I just said, the only products of complete combustion are carbon dioxide and water, as long as your fuel contains only carbon and hydrogen. Another example down here is methanol. This is a fuel that's used in Formula 1 cars. So methanol, in this case it's an alcohol rather than just a hydrocarbon. So methanol plus oxygen goes to carbon dioxide and water. So it's another example. Obviously there's energy released here. This is an exothermic reaction. That energy that's released is used to power the car. So now we need to look at thermochemical equations. So a thermochemical equation shows a balanced equation with the states of the reactants and products and also the enthalpy value. The enthalpy value we talked about a little while ago is the difference in energy between reactants and products. Now because we're exclusively looking at thermochemical equations here in the case of combustion, the enthalpy value is going to be negative because that indicates an exothermic reaction. So you need to show the sign of delta H, you need to show the states, and the states for the reactants and products are solid, liquid, gas, and aqueous. The reason why you have to show the states is because if you have a substance that can exist in two states, so water for example could be liquid or a gas or a solid even, the amount of energy required to do either of those and produce any of those states is different. So by showing the states we know what the amount of energy required specifically for the reaction that we're showing. So let's do an example here. We're going to do the burning of hydrogen gas. So burning hydrogen in oxygen. So hydrogen gas plus oxygen gas, and the product there, well, we don't have carbon dioxide, we've got only water, so H2O. Now I looked up the enthalpy value for this reaction. You'll be told the enthalpy value, and this is an exothermic reaction. It gives off heat and light, so that's going to be a negative value for the delta H. We need to make sure it's balanced, so we've got 2 hydrogens here, 2 hydrogens, that's okay, 2 oxygens, only 1 oxygen. So we need to double that one, so we get twice as much. So now we've got 4 hydrogens, so we need to double this one. Now we need to do our states. So we've got gas for hydrogen, gas for oxygen, and then water here will be liquid. Now, if you did this, normally you would produce gaseous water because it's quite a high temperature, but we're assuming the single conversion to liquid, and that gives us our specific enthalpy value. So let's have a look at some other hydrocarbon fuels. So here's butane being burnt in a cigarette lighter. So butane plus oxygen goes to carbon dioxide and water. Now in this case, we've doubled everything so that we get a whole number ratio for all of our reactants and products. You don't have to do that though. So you could have, rather than having 2, you can divide everything by 2, and you get 1 butane, 6.5 oxygens, 4 carbon dioxides and water. Both of these are acceptable. It's important to mention that these aren't thermochemical equations because we don't have a delta H value. Let's have a look at octane down here. So down here, guys burning petrol. So octane is burning an oxygen, produce carbon dioxide and water. Now everything there is doubled again to get a whole number ratio. So what I'm going to do instead is I'm going to just divide that down by 2. So we get C8H18 plus. Now, rather than doing it as a decimal, which we've done here, we could do this as a fraction. So we'd call that 25 on 2 oxygens, and that goes to 8 carbon dioxides and 9 waters. Now whenever you do an equation you should check that it balances out. 8 carbons, 18 hydrogens, 9 times 2 is 18 hydrogens. Okay, total oxygens, if we look on this side, we'll start over here. So 8 times 2 is 16, 16 plus 9 is 25, and we're doing 25 divided by 2 because each oxygen comes in a packet of 2. So if we divide that by 2, we get 25 oxygen atoms in total. So that all works out. Let's do some examples now. So we're going to start with heptane. Now, off the top of my head, I can't remember how many hydrogens there are in heptane, but I know how many carbons there are. There's 7. So I'm going to draw it first. 1, 2, 3, 4, 5, 6, 7. Put in my hydrogens. 1, 2. Okay, now I'm going to count them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So my equation is going to be, so we've got C7H16 plus, we're going to react that with oxygen, goes to, we're assuming complete combustion, carbon dioxide and water. So now we need to balance. So we've got 7 carbons and only 1 carbon, so we're going to do 7 over here. 16 hydrogens and only 2, so we need 8 of these. Now my total number of oxygens, I've got 8 oxygens plus 14. 14 plus 8 is 22. So it means I'm going to have 11 oxygen molecules. Now I need to put in the states. Heptane is a liquid at room temperature, I believe. Oxygen is a gas, carbon dioxide is a gas, and water is a liquid. Now I need to put my sign on my delta H value, so I've got my magnitude, but I need to put my sign on there. Again, this is exothermic, so it's going to give off energy, so we're going to have a negative value there. Now let's do ethanol. So again, ethanol, we're going to go straight to the enthalpy value here. So we're burning ethanol, that's going to give off heat energy. So it's a negative enthalpy value. Ethanol CH3CH2OH plus oxygen goes to carbon dioxide and water. Again, so our number of carbons here is 2, so we're going to put 2 in front of our carbon dioxides. Number of hydrogens, 1, 2, 3, 4, 5, 6. Over here is 2, so we need a 3 out the front there. Now how many oxygens on this side? 1, 2, 3, 4, 5, 6, 7. So if we do 3 here, 3 times 2 is 6, plus 1 is 7. So now we're balanced. Now I'm going to put in our states. Ethanol is a liquid, oxygen is a gas, carbon dioxide is a gas, water is a liquid. Okay, so there's my thermochemical equations. So those equations there for the complete combustion of a fuel. If you don't have enough oxygen present, you don't get complete breakdown of your products. And what that means is you don't get just carbon dioxide and water being produced as products. You get carbon, particulate carbon, which is also known as soot, and carbon monoxide being produced. And these are harmful, and we'll look at why they're harmful shortly. So, like I said, if you don't have enough oxygen present, you don't break all the bonds in your reactant. And that means you get some bonds being unbroken, and that results in things like carbon being produced, where you don't reform bonds between carbon and oxygen, and carbon monoxide, where again you don't have enough oxygen there, so you only get 1 oxygen instead of the 2 being attached. We can see the result of that over here. So here we have something on fire. There's a guy on a motorbike. This black stuff, the smoke, a decent amount of that smoke is going to be soot, so that's the small particles of carbon. Carbon monoxide will also be produced over here, but you can't see the carbon monoxide. It's a colourless gas. Anyway, so down here we got an example equation for a incomplete combustion. If we look here, we have 9 oxygens, whereas back here where we had octane previously, we had 25 on 2, so 12.5 oxygens. So we've got 2.5 fewer oxygens here, and because of that, we don't have enough oxygen to completely break up the octane chain. So we're getting carbon monoxide as well as the carbon dioxide and water being produced. So as we saw before, a Bunsen burner is a really good place to see this. The reason for that is you can change the amount of oxygen that's present in the Bunsen burner flame very easily. When you start the Bunsen burner, you close the air holes down the bottom. That means not as much oxygen is reaching the flame. And therefore, when the methane burns, it burns incompletely, and you get this yellow flame. When you open the hole down the bottom, you get more oxygen coming in, and that means you burn the methane a lot more efficiently, and you get more heat being produced. So this is our heating flame that we use because we're adding more oxygen to it. Now, in year 8, you might have done the experiment where you looked at how sooty a Bunsen burner flame is. So it's sooty, you put a watch glass over it, and we get a lot of soot depositing on it, whereas if you do the same with the clean Bunsen burner flame, you don't see that. So let's look at why the products of incomplete combustion aren't great. One of them is carbon monoxide is a deadly gas. It is a poisonous gas. It doesn't have a smell, it doesn't have a taste, so you don't know if you're breathing it in. The reason why it's bad is you have this protein present in your red blood cells called haemoglobin. And in haemoglobin there's some ions that hold on to oxygen and carry the oxygen around your blood. If you breathe in carbon monoxide, you replace the oxygens on the haemoglobin with carbon monoxide, and they don't come off. So you get this irreversible binding of carbon monoxide to the haemoglobin. What that means is your cells don't get enough oxygen, and so as the blood is carrying around your body, so your cells start to die off, and that can kill you. So carbon monoxide is not a very good thing to breathe in, because it will irreversibly bind to your haemoglobin, and that will stop you from your cells getting oxygen, and that will kill you. So as a consequence of that, if you're burning anything, you need to make sure that you have lots of air available so that you're not just breathing in the carbon monoxide being produced by the flame. So the other bad byproduct is soot. So this is a carbon particle that's about 10 microns across. So here's the micrometer here, so sorry, 10 micrometers. So this is called sub 10 micron soot, particulate soot. The problem with this stuff is if you breathe it into your lungs can't kick it out because it's too small. So it just deposits in your lungs and goes deeply into your lungs. So it's a respiratory irritant to start with, because if you breathe in lots of soot, you'll be coughing that up, or trying to cough it up to get it out. But the amount of soot that you breathe in over your lifetime increases your chances of getting lung cancer. Reasons for that, it's deep in your lungs, it causes irritation in your lungs, so your cells try to fight it. If you've got too many cells reproducing, that can increase the chance of cancer. If we look at cigarette smoking, for example, if you smoke cigarettes, you get a lot of carbon monoxide and soot going deep into your lungs. And tobacco is particularly good at carrying radiation from the soil in which it was grown. So you get these small particles of carbon which are radioactive going into your lungs. That increases your chances of cancer as well. So the longer the carbon chain, the more oxygen you require for complete combustion to occur. And this is because you simply have more bonds present in your carbon chain. So the more carbon bonds present, the more oxygen you need to break the bonds between the carbons and the hydrogens, and using your oxygen to do that, you produce your carbon dioxide and water. If you don't have enough oxygen present, then you don't get all those bonds being broken, and that results in you producing your carbon and your carbon monoxide. So here's an example down here. There's a trend in the United States for people to buy these diesel trucks, utes. They modify the car so that they can dump all their diesel into the engine really quickly, and that causes a whole heap of smoke to come out the back. This is bad for a few reasons. One, you're producing all this particular carbon which you don't really want to breathe in. But two, it's very inefficient. You're not using, when you're not completely combusting, you're losing energy. You're not getting all the energy out of the fuel that you possibly could. So because of that, it's inefficient. You're wasting money, and it's also bad for the environment. So you're wasting money because you're not getting as much energy out of the fuel as you're paid for. So diesel is a fairly dirty fuel because of this reason. Because it's got longer carbon molecules, you need more oxygen to break it up to release all the energy from it without releasing carbon monoxide and soot. So let's have a look at some questions. So several pollutants are produced in the engines of motor vehicles. Explain why carbon monoxide is produced in the engines of motor vehicles. So if there is insufficient oxygen present for the fuel there, incomplete combustion will occur, and one of the products of incomplete combustion is carbon monoxide. The second question here says, one unburnt hydrocarbon, C6H6, is converted into carbon dioxide and water, releasing 3,280 kilojoules of energy per mole of liquid, C6H6. Complete the following equation. Now, it's thermochemical, so that means we have to have our states. So we're told that this one's liquid, oxygen's a gas, carbon dioxide's a gas, and water is a liquid. We need to put in our enthalpy value, so delta H equals. Now, this is combustion here, so it's going to be negative because we're giving off heat energy. So it's exothermic, so 3,280 kilojoules per mole. Okay, now we need to do our balancing. So 6 carbons, 1 carbon, so we need 6 of these. 6 hydrogens, 2 hydrogens, so we need 3 of these. Now our total number of oxygens, 6 times 2 is 12, plus 3, 12 plus 3 is 15, so we're going to have 15 on 2 oxygen gas molecules. So that's 15 oxygen atoms in total, but oxygen comes in packets of 2, so it's 15 on 2. So today on Flipping Science, we'll do complete and incomplete combustion, as well as thermochemical equations. That's it for Flipping Science today. See ya.